live. Alright, you're live. Cool. Hey, how's it going, everybody? So, welcome back. Hello, hello. Guten Abend. And, hello. So, we're here to solve this problem now. We've got something going on here with my hard disk. I'm moving about almost 180 gigabytes to my external hard disk, so I'm not going to use the mouse while that's happening because I've only got so many USB ports on my laptop here. But what we can do is take a look at this problem. I haven't looked at it yet. It's HackerRank Encryption, HackerRank problem, medium problem, as you can see, and it's called Encryption, and we'll see start to finish how we do from having not looked at this problem at all to right now. So it's a start right now. So let's see. An English text needs to be encrypted using the following encryption scheme. First, the spaces are removed from the text. Let L be the length of this text. Then, characters are written into a grid whose rows and columns have the following constraints. Square root of L, the floor of the square root of L is less than or equal to row, less than or equal to columns, less than or equal to the roof of the square root of L, where this is the floor function, this is the ceiling function, or the roof ceiling, however you want to call it, ceiling function. So the floor of L, the square root of L, and the ceiling of the square root of L. And the rows will be less than or equal to the columns. And so you've got characters are written into a grid. So the spaces are removed. Let L be the length of this text. I guess the text after you've removed the spaces. And you're going to write these characters into a grid, and the rows and columns have this constraint. The number of rows. So it could be that, okay, so these rows and columns, there's always going to be at least as many columns as there are rows. So if there's any extra columns, then anything extra, there's going to be extra column, and it's bounded. Both of these values are bounded between the floor and ceiling of the square root of the length of the text. So it's very close to a square matrix, square grid, I think is what they're communicating here, but not necessarily. So you could have like a 3x4, or a sort of n by n plus 1. N rows and n plus 1 columns, or you could have n rows and n columns. Like if the square root of L is if L is a perfect square, then row is going to be equal to column, and which is going to be equal to the square root of L. But if L is not a perfect square, then row is going to be probably equal. It could be that the row and the column are both equal to the ceiling of the square root of L, or it could be that they're both equal to the floor of the square root of L. See, that it's not clear. It could be n by n plus 1 by n plus 1, or n by n plus 1. N by n, or n by n plus 1, or n plus 1 by n plus 1, if it's not a perfect square, L. Interesting. Okay. For example, the sentence, if man was meant to stay on the ground, God would have given us roots. After removing spaces is 54 characters long, 54 is between 7 and 8, and so is written in the form of a grid with 7 rows and 8 columns. Oh, I see. So you've got to have at least 7 rows. Yeah, it's at least an n by n, and then that obviously won't be enough. That won't be enough space, so you would increase to 1 more column. Okay. Interesting. This is kind of an awkward formulation here. Like, this actually isn't enough description for what it actually is. It seems to be, I mean, I was able to infer what they mean, guess and infer what they mean, but it's actually not correct, because this isn't going to be row equal column equal the floor of 54, because then you wouldn't have enough characters. like you would have to truncate the characters. What they're suggesting is that this is a condition on row and column, but the next condition is that all of the characters are present in the grid and the leftover space is just left empty. And you're going to use as few extra rows and columns as possible. So more likely than not, you'll just use one extra column. In fact, it's got to be a choice of the floor of the square root of L squared, which is n by n, or it's going to be the minimum of the floor of the square root of L squared, as one option, then the floor of square root of L times the floor of square root of L plus 1 quantity, right? And then finally quantity squared of floor of square root of L plus 1. And it's got to be the minimum of those values such that L is less than or equal to that value. So there's two conditions. It's one of those three choices such that the minimum of those three choices that also satisfies square root of L is less than the choice you pick. Right, and this is what they say here, ensure that. So okay, they do describe it here. Yeah. Okay, I take it back. This is enough to describe it. Interesting. Multiple grids satisfy the above conditions. Choose one with the minimum area. Got it. Rows, columns. And they said, and actually there's one more condition here too, because you could do row column 7 by 8 or column row 8 by 7. So they also want the rows to be minimized. If you had to choose between 7 by 8 or 8 by 7, you'd always select 7 by 8. I think you have to also add that in there somewhere as well. Well, it may not matter, but yeah, it's kind of interesting. Half the problem is just understanding what they're asking. So what else we got? The encoded message is obtained by displaying the characters in a column, inserting a space. Okay, so you get to create this grid. The encoded message is obtained by displaying the characters in a column, inserting a space, and then displaying the next column and inserting a space, and so on. So you would take this column. Encryption would be take this column, add a space, take the next column, add a space, etc., etc. And if the grid is empty, I guess you keep those spaces as well, and so on. For example, the encoded message for the above rectangle is IMTG, etc. Right, so there'll be eight characters for the first few, right? 1, 2, 3, 4. No, excuse me, number of rows, just 7. 1, 2, 3, 4, 5, 6, 7 characters for the row. And that'll happen 1, 2, 3, 4, 5, 6, a kind of a modular number of times, 6 times. And the last two will have extra spaces. So 1, 2, 3, 4, 5, 6. And then this one, this 8. So you don't actually include the last character, right? So it'll be, instead of 7, it'll be 6 in this one. Characters 1, 2, 3, 4, 5, 6, right? So you expect. Okay, cool. Okay, so 7 6 times, and then 6 2 times, which gives you 7 6 times gives you 42, and 6 2 times gives you 12, which gives you 54, which is what they had up top here. All right, neat. Okay. So we'll keep going. You'll be given a message to encode and print. Function description: complete the encryption function in the editor below. It should return a single string composed as described. Encryption has the following parameters: a string to encrypt, 1 line of the text, the string S. S comprised only of characters in the range ASCII, A to Z, output format. Print the encoded message on the line as described. Have a nice day. Hey NVSC. Right. So Okay, this is interesting. I'm kind of wondering. Yeah, interesting problem. This is the kind of problem you can code up very quickly, I think. This is kind of easy. It'll take me a little bit longer given that I'm still getting my feet wet here with Clojure. And also, I'm not really sure how I would do this if I wasn't using Clojure, because this sort of clause is kind of confusing. Once you've built the grid, printing the encryption from the grid is relatively straightforward. But before that, it's kind of challenging. Also, it may necessarily be. It may not necessarily be the case that you need to build a grid. Although, in theory, once you've already got a string of characters, it's not really much extra sort of space to build this grid. Anyway, it's asymptotically the same amount of space, so it's not really a big deal. But what is tricky is computing exactly how many rows and columns you should have for this grid. Now that is an interesting question. I think what you're going to want is Also, actually, the way this is set up, we don't necessarily need to do. It could be a variable length vector. Yeah, it could be a matrix with variable length vectors, variable length rows, which actually might be appropriate here. May not be a bad idea. I can consider how I would incorporate that. But I definitely do want to think about, if it's not a perfect square, then you're going to be required to have n by n won't be enough, right, of the floor. So if it's not a perfect square, you're going to need n by n plus 1 or n by n plus 1 squared, where n is the floor of the square root of L. And is it possible that the floor of the square root of L times the quantity squared plus the floor of the square root of L, is it possible for that to be less than L? Think about that for a second here. Also, did we finish moving? We did. Okay. So this is now on my backup. We can close this. We can remove this machine. We can delete these recordings. Let's actually eject this. So that's done. All right. Done. We can reconnect my mouse. Just give me a second while I do that. I like to use my mouse. And what we've got left here is, yeah, I think you can prove it that I want to use the mouse because I'm going to use my doing these things in tandem here. I want to use this notepad. So HackerRank notes will do encryption. And then we're also going to say yeah, so we want to say square root of L floor squared plus square root of L floor. Is that ever less than L? Well, in order for that to be true, you could say L is equal to the square root of L squared, right? And we know that, so this is, right, square root of L times square root of L plus 1. So the thing is, we know that this is always larger. Square root of L squared floor, no. This is always greater than L, necessarily, right? We know that's true. How can I show that this, I want to say if this is true, then we have a contradiction, right? So let's try that. Let's prove by contradiction. So suppose that this is true. Yeah, suppose this is the case. Right? If this is true, right, if this is true, what does that imply about L? Well, that would mean that does that mean? Well, you know what we can do? We can maybe do something like this. We would subtract subtract 3 of these and do square root of L. And we can also do let n equal, or just x, the floor of the square root of L, just because this symbol is kind of awkward to draw. So x squared minus 2x plus 1 is less than L minus 3x. And that gives us x minus 1 squared is less than L minus 3x. Gives us x minus 1 is less than the square root of L minus 3x. And then x is less than the square root of 3x plus 1. Or even another way of looking at it, just subtract L from this side. Well, can we write L in terms of x? Let's do that. Actually, it's better. That's kind of the issue, is we need to relate L and x. So we have x squared plus x less than L. And what's the relationship between L? Well, L, if L is not a perfect square, then floor of square root of L, or x, is strictly less than the square root of L, right? So we know that x is less than the square root of L, which implies and x plus 1 is greater than the square root of L, right? Okay. Fine. Now, is it possible for, I think it is actually possible for x times x plus 1 to not be greater than L. Hold on, we get x squared is less than L. X plus 1 squared is greater than L. Then we get x squared plus 2x plus 1 is greater than L. So x squared is greater than L minus 2x plus 1. But x squared is less than L. So x squared is less than L, but greater than L minus 2x plus 1, which means that L is greater than L minus 2x plus 1, which implies that 0 is greater than 2 minus 1 plus 1, which gives you 2x greater than 1, right, which is if you were to combine these things, oh, so this is true as long as x is greater than a half, which it always is if it's non-zero, if it's non-zero, or if it's a whole positive integer. So that's fine, but if we have this contradiction, right? So now we have x squared plus x is less than L, and x squared is less than L, and x plus 1 squared is greater than L, which gives you x squared plus 2x plus 1 is greater than L. Then we have x squared plus x is greater than L minus x minus 1, and x squared plus x is less than L. There we go, that's interesting. And that gives us L is greater than L minus x minus 1. It gives us 0 is greater than negative x minus 1, which is always true, actually. That means that x is greater than negative 1. It's not a contradiction. It's always true. It's not always true. Wait, what? What's going on? Uh-oh. What the heck? I don't really have a proof for this, huh? Yikes. Yikes. Well, it's not clear to me that knowing that x squared is less than L and then x plus 1 quantity squared is greater than L would imply that x times x plus 1 is either greater than or less than L. Like, how do I know? Are there cases where it's less than L? Is that even possible? Like, I don't know, if you had like 99 and take the square root of 99, right? Oh, what's going on here? They changed this? Square root of 99 is 9. Floor of that is 9. Oh, you're right. 9 times 10 is 90. Oh, yeah. it's definitely possible for this to be less than L. Oh, excuse me. Is it always less than? I don't think so. I don't think it's always less than. Wait, really? 54. It's like 7, right? It'd be above. So we do 7 times 8. But if you were really close to 64, like 63, right? 7 times 8 is way below 63. Oh. Right. Okay. So I take it back that it's not clear at all what the conditions are for when it's actually more nuanced than that. It's you're not going to be able to prove this algebraically. It's impossible. Or x times x plus 1 is greater than or equal to L. Amazing. Amazing. So basically you've got to decide between x number of rows or x plus 1 number of rows, but you're always going to have x plus 1 columns. Interesting. Very interesting. Okay, that's fine. Can make that decision. It's a relatively straightforward decision to make. Alright, so this has been deleted. Really kind of cool, interesting question. But yeah, it's like if it was 56, then you would need to use over 56, but less than 64, the number, then you would need to use 8 instead of 7. You'll never use 7 by 7 unless it's a perfect square. Okay, so there's a little bit of logic you have to do where we actually decide how many rows and columns. Yeah, use exactly the floor of the square root if it's a perfect square. How do we know if it's a perfect square efficiently, though? That's another question, that predicate. Is perfect square closure? I've seen hold on. There's a couple things here. No, so knowing if actually you could tell if it's a perfect square if when you take the floor of the square root and then square it and it's equal to the original integer, then that's perfect square. Wait, is that like a really efficient way to determine if something is a perfect square? Take the square root and then take the floor of that square root and then multiply the two that multiply it by itself, the result, and if that's the number you started with, then it's a perfect square. Wait a minute. What? No, well, I guess it's not that efficient because that's susceptible to floating point error. It's not really. There are other ways to do it. There's, I think there's a Newtonian sort of iterative method you can use to check if a number is a perfect square. And then there's, I think that's the way to do it. There's also a built-in in Python, I think, to check if something's a perfect square. It's pretty funny though. Wow. Nice. There's another way to do it too, is using a summation of odd numbers. If you keep adding odd numbers, you'll always get a perfect square, which is kind of weird how that works. But is that true? Wait a minute. 1 plus 3 plus 5 gives you 9. Plus 7, yeah, it gives you 16. Yeah, it works. I forget why though. It's kind of wild, but you can at least prove it inductively. That it's always a perfect square. How would you do it if you had? What's the inductive proof? It would be, suppose that a sequence of odd numbers being added together is a perfect square. Then add the next odd number, and then you end up with x squared plus 2k plus 1, where, right, so that could be refactored to x plus 1 squared, which, as long as k is equal to x. Oh, that's wild. That's so cool. Which you can show that property holds inductively. So it's like the nth, if the sum of the first n integers, odd integers, gives you n squared, right? First 2 integers gives you 2 squared, right? First n integers gives you, n odd integers gives you n squared. Then adding the next odd number, which is n plus 1, or no, am I doing it right? Yeah, first n integers, so adding, which would be adding 2n, to be 2n plus 1 is the next odd number. If you add that to n squared, then you get n squared plus n, 2n plus 1, which can be factored to n plus 1 squared. And then the sequence is just the n plus 1 odd integers. First n plus 1 odd integers. Assuming the nth odd integer is 2 times n plus 1. I have to show that that's true as well. Which I think it is, right? The first odd integer is... No, it's actually 2n minus 1. Oh, right. It's more like the 0th integer. It's a little confusing, but it does work. I'm fairly certain. You got to work it out though. You got to word it correctly. It's the reason is the nth integer, nth odd integer, which is sort of 0 times 2 plus 1 would be the 0th, and then 2 times 1 plus 1, the 3 would be the first, right? So from starting with 0 index, gives you n plus 1 quantity squared. So the 0th number would be, right, 1 squared, and then the first would be 2 squared. 1 plus 3 gives you 4. So it gives you n plus 1 quantity squared. Then you can consider nth from the 0 index. Then the third, so third from the 0 index would be 3 squared, would give you three integers added. So you could say that there's some sequence of n, the first n odd numbers would give you n squared, would be n squared, because it would be starting, it would be n plus 1 squared, but where n is the 0th index. And then adding the next value, the next odd number in terms of the first, so the n plus 1th odd number is exactly, I think, 2 times n plus 1, right, where n is that index. Does that make sense? The n plus 1th odd number in this scenario. It's just 2n plus 1, right? Because it's 0 index, so you subtract 1 from that index, so it's n, and then the odd number makes it 2 times n plus 1. It's confusing, but that's why it works how it works. The inductive step. It's 1, 3, 5, 7. For instance, the fourth number would be n is 3, and that would be 2 times 3 plus 1. Yeah, exactly that. The n, where n is 0 indexed. It's the nth number, but it's the 0 indexed version of it. So it'd be the n plus 1th number is really n equals n is n rather than n plus 1 to give you the n plus 1th. Yeah, that's kind of confusing. That part is like, it'll throw you off, but that's effectively why. Pretty interesting. Anyway, so why am I babbling on about that? That's another way to check if a number is a perfect square, is you can use a sequence of odd numbers. So you can show that if you subtract the next largest perfect square, or if you subtract a sequence of perfect squares, something like that, if it's an odd number, so the next smallest perfect square, if you subtract that and then you show the result is an odd number, that will tell you if it's a perfect square or not. That's kind of a faster approach than using the Newton's method, iterative method. Or that's kind of interesting. What would that look like? That would be like, given some L, you can say, okay, let's take L. So if L is not a perfect square, you say the number that's less than it, L minus 1, and then you take the square root and the roof of that, ceiling of that. Now, how do you know which neighboring perfect squares there are for a particular L? How do you find X such that because if you knew X in this instance, basically you can show that L is either X squared or X plus 1 squared. If L is between these two, like if we did L minus X squared is equal to some 2k plus 1, where k is an integer, if you knew that this is odd, this difference. No, see, that doesn't work either, because it's got to be the right. It's got to be the right odd number as well. It can't just be an odd number. It's got to be the odd number. In other words, if you did like 64 and 6 and, well, no, actually, yeah. Well, 64 minus that's 8. 749 is 15. 8 squared minus 7 squared should give you 15. Which is exactly 2 times 7 plus 1. Yeah, actually, you're not even checking if it's odd. You're checking if it's exactly this number. So this difference, then that implies that this thing is a perfect square. But the problem with that approach is you have to find what this is. This is supposed to be, which is not obvious, right? If you did like, if you did like 64 minus 1 square root, maybe floor is what you've got to do. That would give you 7, I think. Yeah, because this would be 64 minus 1 would be less than the square 8 squared. So when you take the square root, it's going to be a number less than 8. And so you take the floor, it ends up being 7. And then you would check if this is equal to, if so you have like L, the floor of the square root of L minus 1, let that be T, and then you check that L minus T squared is equal to 2 times T plus 1. Right. That's what you would check if it's a perfect square or not. But now you're invoking this perfect square function, the square root function. And this is not really as susceptible to floating point error because the larger the number is, it'd have to be like a really big number for this L minus 1 square root floor to not be to not go to the next smallest integer. I don't know. It's not really foolproof either, though, is it? I don't know. Maybe it is better to use Newtonian method. There's like an iterative Newtonian method. We could look it up to see perfect square closure. Newton method. Not computing square roots, but integer square root. Yeah, so this has cycles in it, but that's fine. As long as you break the cycles, you're fine. Can you use binary search? Oh yeah, how do you use the binary search? You can use a binary search. Integer version of Newton's method of square root. Oh, interesting. Faster than binary search. How would you use binary search to find determine whether or not it's a square root? Oh, I think I understand. You basically would say, so you have some L, and you say, I guess what you do is you just keep squaring your value until you're larger than L. No, how would you do this? So you have some, I guess you start with, you know, I equals 1. And you say, is I squared less than L? If it is, or if it's equal, less than, equal to, or greater than. If it's equal, you're done. If it's less than L, then you got to do something smaller. L's not a positive integer in this case, so we don't have to worry about that starting off. But if it's something larger, then in this case, you've got to go to smaller I. Oh. In this case, larger I. But the problem is, how much larger are you supposed to make your I, and how much smaller? Like, where are you supposed to? Usually there's some range that you're iterating over with binary searches. How does this work? You could just keep squaring the thing until you're larger and do it that way. So you'd have like I squared, I to the 4th, I to the 8th, etc. For some I guess I is 2, so it would be like 2, 4, 16, 256, etc. And then, you know, you can figure out where L is with respect to this, and that can maybe give you an idea of which square, right? Because all of these are square, perfect squares. So you could do starting, yeah. Unless you're binary searching over a set of perfect squares, you could do that too. That would give you sort of a, well, I mean, the iterative approach gives you square root time, square root complexity, right? That would just be keep incrementing some base value by I until the square of it is less than what you're looking for, or is greater than what you're looking for. Alternatively, right, you could just keep squaring the base as well. That gives you, or even doubling the base, which is what you're doing here. Go, yeah, 2, 4, 8, 16. That can give you a logarithmic time where the square, you could figure out between which of these, you know, if you're between 16 and 256, that means you're between 4 squared and 8 squared. And then you can do binary search over this set of numbers to figure out, you know, which one is smaller, which one is larger. And let's say L is like 64. Excuse me, this is 16. Although there's a lot of numbers in between here, these perfect squares. Yeah, and then you can figure out, you know, okay, this is between 7 squared and 8 squared. Although the problem with this is, the number of numbers between 4 and 16, even though there's a squared operation in between, there's a lot of numbers. It's potentially the difference between 2 raised to the n plus 1 and 2 raised to the n, which that difference is still very large. It's actually just 2 raised to the n. So even if you take the logarithm of 2 raised to the n, it's still a linear amount, which is kind of the problem. So it actually doesn't really save you much. You could just still do the for large n. You might as well be doing like a linear search, square root of n search. What does that look like? Binary search for perfect squares. Hello ACM. Perfect square. Eventually we'll have to. Oh yeah, I think I've looked at this in the past. I've looked at this a few times, but for whatever reason it seems new to me each time. Binary search. Search space is narrowed by half. Okay, but how do you do this? Oh, I see. Oh, I understand now. Got it. I feel kind of dumb doing this now, thinking about this now. Alright, the range of numbers is actually, because you know that L is going to be less than L squared for all positive integers, you can just binary search between 1 and L squared. Oh, I see. Got it. And just keep squaring this number until you find, okay. Never mind. Got it. The mid square could overflow. 64 bits. This could overflow. I see. I really need to use the bathroom. Not easy to get it right. I actually really need to use the bathroom suddenly. Okay, that's what they mean by binary search. Got it. I totally messed that up, missed that. I should implement that. Let me like actually end stream, go use the bathroom, come back and implement that. But yeah, so we'll implement a binary search, I guess, in Clojure for the, is it a perfect square or not? If it is a perfect square, then well, this probably is one for already that exists for Clojure. Clojure is perfect square, like a math library for Clojure. Number. Perfect square. Clojure. Max Clojure. Recursion. Tail recursion. Oh yeah, you're not supposed to do recursion without recur, otherwise you're going to blow the stack. Functional reduce, yeah. Sneaky, blows the stack but not as easily. Trip math library. Interesting. And I wonder if I can actually require libraries in from the HackerRank's sort of IDE Clojure libraries. I wonder if I can do that, if it works. And I really need to use the bathroom, but I want to end the stream to kind of keep the videos short. So yeah, this is really more of just a discussion about perfect squares. But it looks like there's not really an obvious math library for Clojure. I don't know, is there like a Clojure math library? Clojure math library, built-in library. Yeah, we'll come back to this. We'll read this. I actually really gotta go. I gotta go like now. So I'll be back. Thank you for watching. I didn't really do much this time around. Just kind of poked around at perfect squares, pondering perfect squares in Clojure. But I've got a pretty good sense of how this can, what we've got to do here, and then programming it shouldn't be too hard. So we'll come back to this. Let me end the stream, and then I'll change the description. Or yeah, I'll just end stream and then edit the live stream description later. So I'll be back. Thanks for watching.